Hello, my name is Ming, and I'll be presenting our work on unsupervised learning for long-form video using structured optimal transport. So we begin by introducing a task, this temporal action segmentation task in computer vision. And the goal of this task is to assign the frames of a video to one of k action classes. So here's a cartoon illustrating that. We have a video, we feed it into a model, and the goal of the model is to classify each frame to an action class. Here's an example of videos typical of this task. So this is an instructional video of how to perform CPR. And important characteristics of videos typically encountered in this task is that they're long form, so they can be several minutes rather than a few seconds long. And also these are multi-stage videos where you see multiple classes happening within a video. And so typically we see assembly and instructional videos being evaluated on in this task. So this is very challenging for existing machine learning methods. Now we're going to approach this fully unsupervised, no annotations, using an approach based on simultaneous learning and clustering. And so how do these methods work? Well, these methods jointly learn both representations and labels from a dataset. And the idea is to alternate between label generation and learning using these labels. So this cartoon illustrates that. We have these learned representations which come from the training data. We use them to generate pseudo-labels, and the pseudo-labels are used to refine the representations. And there might be some interpretation that we're really solving an auxiliary task based on clustering. And a fundamental question, a very important aspect of these algorithms, is how we generate the pseudo-labels. So here's an example. This is reasonably well known, the deep clustering paper, where we are encoding images through a ConvNet. We cluster the learned representations using k-means. And the cluster assignments become the pseudo-labels, which is then used to train the network. This was extended, Seller, and instead of k-means, Asano et al. Use optimal transport for the pseudo-label generation. And this is roughly the approach that we use in our work too, but for videos. So optimal transport for pseudo-labeling, how does it work? So suppose we have n training images and k clusters or classes. We're going to solve this constrained optimization problem to determine our pseudo-labels. So T is our pseudo-label matrix. And really, the pseudo-labels are determined by minimizing the total label assignment cost over the dataset. And this cost matrix C can be easily determined, say, by taking the negative of the logits from the fully connected layer. And it's subject to constraints too. These are called the balanced assignment or equipartition constraints. And the interpretation is straightforward. So the first constraint says that each image must have a label, must be assigned to a class. And also, the second constraint is saying that, well, the pseudo-labels actually must be evenly spread across the clusters. So each cluster would have n over k samples assigned to it. And the constraints are very important. It actually prevents collapse of the unsupervised learning algorithm. At least this constraint, the second constraint, does. Now, these approaches actually work very well for image classification datasets, where we have these unstructured image collections. And also, we have these balanced ground truth class annotations. So for example, ImageNet, CIFAR, there is some underlying ground truth annotations, and they are actually balanced across classes. Finally, we'll comment that optimal transport is actually very efficient. If we apply entropy regularization, we can use a sync-or-nop algorithm, and it's easily implemented in PyTorch and very amenable to GPU computation, and it scales to really large datasets like ImageNet. Now the question is, does this work for the action segmentation task with videos? Now, really, we actually just have an image dataset, right? The images come from videos, but they're still images. But what has changed? Well, before we had this unordered image collection in the image classification setting. For videos, we actually have this unordered collection of videos. But each video has structure. It's a structured collection of images. And we would argue that the standard optimal transport method described before, applied naively, has no understanding of this structure. And what do we mean by structure? Particularly, we mean this temporal consistency property where adjacent frames within a video are actually assigned to the same cluster or the same class. And so also another property is we have these long tail class distributions, which happens a lot in these action segmentation datasets. So here's an example of the breakfast dataset. It's videos of people frying eggs and making cereal. We see here clearly we have this long tail action class distribution present. In fact, we would argue it's very difficult to curate balanced classes across video frames when we're collecting video data. So we can actually deploy standard optimal transport for pseudo-labeling. So we'll see what actually happens when we do this. So C here, we've gotten this from a real video, and C are the label assignment costs. It's pretty noisy, it's very imperfect, as you can see. Red lines actually demark the ground truth. And when we apply optimal transport, we get pseudo-labels which look like this. So yellow is high and blue is low. And so does this satisfy temporal consistency? Clearly not. And also, does this address the long tail class distribution issue? It's hard to tell, but it certainly doesn't. It's actually balanced across clusters here. So how do we fix this? Well, previous approaches, and here's an example by Kumar et al. For the action segmentation setting, applies regularization. So here again, we have a cluster assignment matrix, and x-axis, by the way, is time, and we can actually add a temporal regularization term to this cost matrix to get this regularized cost. And you can see the temporal regularization is trying to bring the pseudo-labels into this sort of diagonal pattern. And so what happens? We get pseudo-labels which look like this under this approach. But does this fix temporal consistency? I would argue not really. And also, are we fixing this long tail class distribution issue? Definitely not. It's still balanced across classes. And in fact, there are assumptions required for this approach. You're assuming that the action classes always occur in the same order within a video. And so this doesn't hold in general for these data sets. So, core methodology. This is our approach. We're actually going to move away from standard optimal transport and use this idea of structured optimal transport to generate the pseudo-labels. And so in particular, the technical term is we're going to use this unbalanced fused Gromov-Wasserstein formulation, where we're going to take these properties we want. So temporal consistency is going to be addressed by a Gromov-Wasserstein term, and the long tail class distributions will be addressed by incorporating unbalanced transport into the formulation. So Gromov-Wasserstein, how does this work? How do we use it to encode structural priors like temporal consistency? Well, if we take the standard optimal transport we introduced before and we adapt it to a Gromov-Wasserstein or GW problem, it's going to look like this. So notably, the constraints are actually still the same, but the objective function has changed. And in particular, before we had a single cost matrix C, and now we have two cost matrices in the GW setting, CV and CA. And also we need to define this loss function between elements within the cost matrices, so between both cost matrices, L. And we'll declare this in a moment. Importantly, the reason why this can account for the structure is rather than having a linear objective function like before, we have a quadratic objective. And in general, this is non-convex. And this quadratic term allows us to encode temporal consistency, as we'll see soon. So we go back to the case. Let's suppose we have a single video and we have n frames and k action classes. It's going to look like this, our CV and our CA matrices. So CV is a banded diagonal matrix, which looks like this. It's n by n, so the length of the video. So it's a sparse matrix, banded diagonal with zeros on the diagonal. And CA is actually this dense k by k matrix. K is the number of classes, and zeros on the diagonal. This can actually be implemented very efficiently. So CV, if you think of this as a linear operator, can be implemented using 1D convolutions, and CA can be implemented using like a sum. And L is our loss function, and we just set this to be the product. And the objective function actually simplifies to this nice inner product form rather than that big sum. And the intuition of this Gromov-Wasserstein term is actually very simple, that inner product form. It basically penalizes the case when adjacent frames are labeled to different clusters. So it's basically penalizing any configurations of pseudo-labels which are not temporally consistent. So what happens? So we have a label assignment cost. We generate pseudo-labels. This is what we did before using standard optimal transport. When we include Gromov-Wasserstein, it looks like this. And so temporal consistency, definitely, but the labels are still balanced, unfortunately. And so we address this by unbalanced transport. And really, so in the context of standard optimal transport, we're going to replace the constraint here over class distribution with a penalty. And that's enough. So lambda is a hyperparameter which is set to reflect the level of class imbalance in the dataset. So very long tail, you want to set lambda low. Now, this is our pseudo-labels from before, which are balanced, and this is what happens when we include unbalanced optimal transport. And so this is our action segmentation optimal transport, or ASOT pseudo-labels. And you see this matches the ground truth a lot better, and action classes are missing in the pseudo-labels. So it definitely has temporal consistency and addresses long tail class distributions, which is great. This is what we wanted at the onset of the project. So action segmentation optimal transport, concretely, we're going to solve this optimization problem. So again, different from the standard optimal transport formulation. Really unbalanced transport is in the orange, and Gromov-Wasserstein, the temporal consistency part, is in the blue. And green is our standard optimal transport bit derived from the learned representations. Now, it's still very fast, so we use projected mirror descent to solve the ASOT problem, and it can still be implemented very easily in PyTorch and runs on the GPU, so we have code available, and for a single video, 16,000 frames, 19 action classes, 24 milliseconds on a standard GPU. So, some experimental results. So here's our unsupervised learning pipeline. So it's the same pipeline as before. We generate pseudo-labels using our learned representations, which are used to refine the learned representations. And notably, we have a simple MLP to encode the frame features. So we don't operate on raw images. We use pre-extracted frame features as standard for this task, and the MLP is initialized randomly, not warm started, and we generate the pseudo-labels per batch online. And so this is a cheeky anagram, which we found out after we submitted the paper, that ASOT is SOTA. And CVPR keeps us honest, our method has to work, and it certainly does. So if we evaluate on standard segmentation metrics such as accuracy, MIOU, we also use a F1 score to measure the quality of the segments. We show considerable improvements compared to state-of-the-art, recent state-of-the-art. So typically relatively large margins. And notably, UFSA and TOT, the previous two methods, which newer methods, use standard optimal transport. And notably as well, UFSA has this complex multi-stage transformer architecture to address the limitations of standard optimal transport, which we do directly through the optimal transport formulation. In an ablation study, it's important to note that breakfast has dominant action classes. It's very long tail. And so if we remove unbalanced transport, it makes a big difference to the performance. Whereas for desktop assembly, it makes less of a difference. And as well, the Gromov-Wasserstein, the structural information is very important. It's just fundamental to videos, and it's important across all the datasets and metrics. Some qualitative examples. Our unsupervised learning algorithm generates some pretty impressive results. So notably on the left, breakfast, we see order variations and repeated actions handled in our videos, which wasn't the case for prior works. Finally, we'd like to mention that ASOT is more than just action segmentation. This idea of using structured optimal transport for unsupervised learning is more general. Of course, we can extend this idea of ASOT to the semi and weekly supervised learning settings, as well as their variants, as well as unsupervised domain adaptation. We can use them. It's just pseudo-labeling. We can extend it to image segmentation and monocular depth. So these are different tasks, bigger tasks, but things should still port over fine. And something that we're working on that we're very excited about is actually addressing a different structure matching problem using this technique based on local feature extractors and matches. Finally, we'd just like to comment there's some theoretical results for self-training, and it'd be interesting to understand how our method fits into this framework. Thank you for your attention. Here's a link to the paper, and we provide code as well. And please get in touch if you have any questions.